Hello, welcome to lecture 5 of module 3. This is lecture number 26 of the course. In this lecture, we will continue our discussion on classical regime. Then we will start discussing the so-called quantum regime. But before that, we have to understand quantum noise, as quantum noise distinguishes the classical regime. In fact, to appreciate quantum noise better, we have to understand classical noise first. So we'll have a discussion on classical noise in terms of the so-called classical Langevin equation. So let us begin. In the last class, we started discussing the classical regime of cavity quantum optomechanics with the goal that it will later on help us in understanding the quantum regime better. In the classical limit, we replace the position operator x cap by the corresponding classical variable x, while the light field, which is represented in the quantum regime by the annihilation operator a cap, it is replaced by the coherent state alpha, which is the most classical state of an harmonic oscillator. And we all know that in the quantum regime, the light, which is an electromagnetic field, behaves like a harmonic oscillator. The equation of motion will be in the form of x and alpha, and we have written two equations, for one for mechanics and other for the light mode. The mechanics is modeled by the mechanical oscillator is considered to be a damped harmonic oscillator, and it is acted on by the radiation pressure force. Okay, and the light mode is represented by this equation, which I explained in the last class. As you can see, that the first term on the right hand side of this equation, this particular term takes into account how the light field is coupled to mechanics. The second term refers to decay of the amplitude of the photon, and the third term takes the laser drive into account, and where omega L is the laser frequency. The parameter alpha max here, it indicates the fact that the value of alpha will settle down to the value of alpha max at resonance. So then we got rid of the time dependence in this light mode equation by going over to the laser frame, rotating laser frame, and this is what the transformation we made. After making the transformation, we get an equation with a new light variable, but for convenience we again represent the new light variable by alpha. Okay, and then it resulted in this equation of motion for the light field. Then we define the detuning parameter as the difference between the laser frequency and the resonance frequency of the cavity, and we get an equation for the light mode. And as we analyze it, that in the steady state, when there is no coupling to the mechanics, then it turns out that indeed in the steady state, where alpha takes the value of alpha bar, it actually at resonance take the value of alpha max as we described. And this is the intensity plot versus the detuning parameter at in the steady state, and we can see that this spectrum here has this full width at half maxima is given by this cavity decay rate kappa. Then we try to solve these two equations for the steady state, and we have linearized it around the steady state. And to do that, actually we assume that the coupling between the system and the bath is weak, and here by system we meant the mechanical system, the mechanics, the harmonic oscillator, the mechanical harmonic oscillator, and by the bath we mean the driven optical cavity. Okay, so basically the mechanical system is actually surrounded by the optical field, and which is considered to be the bath, and the coupling is considered to be weak. And in that case we take that the value of alpha is slightly deviated from the steady state value by delta alpha, while the mechanics, the displacement of the movable mirror is uh, displaced from its steady state by an amount delta xt. You can consider them as the fluctuation also. And the next, we have taken certain step to solve it. First we solve it for the steady state, and then we look for the first order parts of the equation of motion. Now assuming that already we know what is the steady state value alpha bar and x bar, we solve this equation of motion, and then we just put replace x by x bar plus delta x and alpha by alpha bar plus delta alpha, and we obtain the equations for the fluctuations, corresponding fluctuations for the mechanics as well as the light field. And we analyzed it, and the idea was to eliminate the light field dynamics and then plug the solutions into the equation of motion for the mechanics. And we have done that. Of course, the idea was to see the response of the mechanical system to an external force. So therefore, in addition to the radiation pressure force, we have added an extra force term here, because we are interested to know how the mechanical system is responding to this external force F here. And then going over to the frequency domain, we discussed all these things in detail in the last class. We got the expression for the fluctuating field for the light field, and in the process we defined a quantity called the cavity susceptibility by this parameter, and which basically gives us the response of the or basically shows us how the light field is getting modified due to the interaction with the mechanics. And the equation of motion for the mechanics is here, it is written here, and then we replace the quantity delta alpha and delta alpha star, which is the complex conjugate of delta alpha. We put it here, and eventually after using this Fourier transform relations, we obtain an expression for delta x. This is basically the response of the mechanical system or the fluctuating quantity, and we were able to write it in terms of a very compact equation. And we have defined a parameter called k of omega, and what it basically shows is that because of the presence of the interaction between the mechanics and the light, the mechanical susceptibility of the mechanical harmonic oscillator is getting modified. So therefore we are having an effective susceptibility parameter. Then the next, we went on to understand what is the meaning of this extra parameter, and it turns out that our analysis finally showed that the real part of this susceptibility parameter is basically, or this k of omega is related to the frequency shift of the extra frequency shift of the mechanical oscillator, and the imaginary part of this term k of omega around the resonance frequency of the harmonic oscillator or the mechanical oscillator is related to the extra damping that is suffered by the mechanical oscillator. So now what we are going to do, we are going to analyze this term k of omega in somewhat details, and then we will be able to extract certain quantitative information about the mechanical system. Here chi c, that is the susceptibility, cavity susceptibility, and it is given by chi c of omega is equal to 1 divided by minus I omega minus I delta bar plus kappa by 2, where delta bar, this is the modified detuning parameter, and this is actually equal to delta plus omega optical by L, and x bar, this is a very small quantity, so in many cases we may assume delta bar to be nearly equal to delta only. We can define another parameter which will simplify the calculation, that is called the optomechanical coupling linearized, rather, because we are now in the linearized domain. So this is called linearized optomechanical coupling strength, optomechanical coupling strength, and you will see that this is going to be a very, very important parameter, and this is defined as z square is equal to h cross divided by twice m capital omega optical by L whole square, then mod alpha square. This is what is z square. So using this parameter z, optomechanical coupling, linearized optomechanical coupling strength, we can rewrite the expression for this capital K omega as follows. That would be I into twice m omega z square chi c, cavity susceptibility parameter evaluated at frequency omega, minus its complex conjugate evaluated at frequency minus omega. Okay, now we can put the value of chi c and its complex conjugate evaluated at minus omega from this expression, and then we can find out from here, we can find out the real part of, because this is a complex quantity, we can find the real part of k of omega and imaginary part of k of omega. A simple straightforward algebra we can do, and if we do that, then you recall that this gamma optical, that means the optomechanical damping term that we obtained was this. It is related to the imaginary part of k of omega, and this was given by 1 by m of omega into imaginary part of this quantity k evaluated at the resonance frequency of the oscillator capital omega. And if we do the algebra, in fact it's very straightforward to see from this expression that this is going to be equal to twice of z square, and then it would be the real part, because this is imaginary quantity is there, so we have to take the real part of this. So this would be real part of chi of c of omega minus chi of c susceptibility, complex conjugate of susceptibility evaluated at minus omega. In fact, of course, we have to take omega is equal to capital omega. If we do that, and this simple algebra, I urge you to do it, otherwise we'll do it in the problem solving session, you will get the expression for optomechanical damping parameter as this one. This would be z square kappa, and a very nice expression you will get by simple algebra. You will get, it would be omega plus delta bar whole square plus kappa by 2 whole square, and there will be another term that would be minus 1 divided by capital omega minus delta bar whole square plus kappa by 2 whole square. So this is the expression for optomechanical damping. Now we can plot this parameter as a function of the modified detuning parameter delta bar, and if we plot it, we are going to get a plot like this. So you can actually use a computer and some parameter, but typically the plot will look like this. So on the x-axis it is delta bar, and here we have gamma optical, there is a damping parameter. So the plot will be something like this. It will be somewhat like this. Okay, all right, this is actually symmetric in a way, anti-symmetric here. Okay, this is what we are going to get, and this peak would be at minus omega, and here it would be at plus omega, and the full width at half maxima. So we are getting basically two peaks, one is in the upward direction, other is in the downward direction, as you can see, and this full width at half maximum is given by this kappa. Okay, so we are getting sharp peak and this is the plot when this cavity decay rate kappa is much smaller than the resonance frequency of the oscillator. On the other hand, if say kappa is much greater than the resonance frequency, then you are going to get a plot something like this. So you will get, this is for this particular one is when this cavity decay rate is much larger than the resonance frequency. So we'll get the dotted one for kappa much larger than the resonance frequency omega, and we will get very sharp peak for kappa much less than the resonance frequency omega. Now let me explain what it physically mean, these two plots. Particularly this one is very important for us, kappa much smaller than omega. You can see that it is very clear that I'm going to discuss the case kappa much less than omega. Here if you see from this plot that for delta bar is equal to minus omega, we have positive damping. So here as you can see, this gamma optomechanical damping, this is greater than 0. So which effectively means that we are going to get cooling. The mechanical oscillator will get cooled when the detuning parameter, when we can have delta bar is equal to minus omega. Okay, on the other hand, in this regime here, for so we'll get cooling for delta is equal to minus omega, and for delta bar is equal to plus omega. So here this one we are going to get heating because we have negative detuning, because gamma optical, that is your negative damping, that so this here will have heating. The mechanical oscillator will get heated up, and on the other hand here we are going to get the cooling effect. Okay, now let us understand it actually what's going on. It's very simple, because if we come up with say delta, our laser frequency, laser has a frequency such that our delta, rather than delta bar, let me just take delta because the correction is very small. So if say delta is equal to minus omega, then it means, because delta you know that is equal to the difference between the laser frequency and the resonance frequency of the cavity. So that would be omega optical minus capital omega. So if the laser frequency is such that this is less than the, this is less than the resonance frequency of the cavity, so in that case quite clearly the laser light cannot enter into the cavity because it is not satisfying the resonance condition. It will go here and it will hit the front mirror and then it will get reflected. However, what happens is that if suppose there are some kind of vibration is there, that means some phonons are there in the say it is a cantilever, so the light field then can, this light field can absorb a phonon, and thereby, so in that case you see, if we'll have omega optical is equal to the laser frequency is omega L, then if it can extract one phonon from the cantilever, then this laser light will be able to enter into the cavity and the laser frequency will be enhanced. So therefore the photon that is entering into the cavity will be now blue shifted, as it has gained energy from the mechanical oscillator, resulting in cooling of the cantilever. On the other hand, when we have this delta is equal to plus omega, you can do the similar analysis, then photon will be able to enter into the cavity if it dump extra energy, because you see it is plus omega, then your omega L is equal to omega optical plus omega. That means now if the resonance condition has to be satisfied, then the phonon has to dump this, the laser light that is impinging on the front mirror has to dump this extra energy, and if it dumps the extra energy to the cantilever, then it will be able to enter into the cavity and circulating light will be there inside the cavity, and in the process the mechanical oscillator will get heated up and the phonon will now become red shifted in frequency. So one thing I forgot to tell, please note that this domain, when kappa is much less than omega, in this case we can have two sharp peaks, and we can these peaks can be resolved, and this is known as the resolved sideband limit. So this is very important. So the domain when kappa is much less than omega, this is popularly known as resolved sideband limit. And in most optomechanical systems, generally people work in this limit because it's very useful for applications. Now let us discuss about the implication of the real part of k omega. As pointed out earlier, it is related to the frequency shift of the mechanical oscillator. So we saw earlier this expression that frequency shift delta omega is equal to minus 1 by twice m omega. Omega here is the resonance frequency, and it is real part of k evaluated at the resonance frequency. So this is basically we know as the optical spring effect. Now plugging the value of k of omega, we can get these expressions very easily, because k of omega, which we have written earlier here, from this expression you see, you will have, if you put that here, delta omega will be equal to minus z square, and this would be imaginary part of chi of c cavity susceptibility evaluated at plus omega, capital omega, then minus of its complex conjugate evaluated at negative of this capital omega, the resonance frequency. You can easily work out the details doing the straightforward algebra, and then it is possible to get a typical plot for the frequency shift delta omega as a function of the detuning parameter delta bar. Let me just draw it here for various cases. So this is my delta omega, the frequency shift versus delta bar. Now in the regime when the cavity decay rate kappa is much larger than omega, the resonance frequency, the plot will look like this. It would be antisymmetric, and it would be something like this. So you will have here, it is for plus omega, and this would be for minus omega, and here I am plotting it for the case when kappa is much larger than capital omega, the resonance frequency. Now as you can see from this plot, two things is clear. One is that this is antisymmetric, and the shift in the frequency is positive, that is greater than 0 when our this detuning parameter delta bar is greater than 0. On the other hand, this delta omega, the frequency shift is negative when we have this detuning parameter is negative, and this is for the case when we are in the unresolved sideband regime, right? Because as I said here, that kappa less than much less than omega is the so-called resolved sideband regime, and this is the opposite of that regime. Now physically what it means is that the mechanical spring in this case, as you see here, delta omega is greater than 0, so therefore the mechanical spring, the spring constant is now enhanced, so therefore the spring is getting stiffer or harder due to the light induced effect. On the other hand, for delta bar less than 0 in this regime, the frequency shift is negative, so therefore the spring constant is getting reduced. That means the spring is getting softer as delta omega is less than 0. Okay, and it has certain issues because of this as regards the cooling is concerned, because we already know that for optomechanical cooling we work in the regime delta less this negative detuning, right, delta less than 0. Okay, just let me again remind you, yes, this is the regime. Here you see we work in the regime where delta bar is less than 0 and we get the cooling effect. So if we are interested in cooling, and if we want to cool the mechanical spring harder, then as a result of, because this delta omega this frequency shift will also increase if we increase the intensity of the laser, and because of that the spring will get more softer, and this is actually going to lead into the instability. So this is not a good thing, but this issue can be circumvented or avoided if we go over to the resolved sideband regime, that is when we have kappa is say much less than the resonance frequency. And in this case the plot is little bit slightly complicated, but still let me try to plot it. So this would be something like this. It will be again here, let me draw it here, it would be antisymmetric, and you will have a peak here and it will pass through it. There will be almost kind of a singularity here, and it will be like this. Okay, something like this. So here you see that we can choose this resonance frequency here, delta. In this case we can choose the detuning parameter exactly at the resonance frequency here, at the negative of the resonance frequency, and when then the cooling will be in this case strong. At the same time we will be able to avoid the softening of the spring, and we will no longer have the optical spring effect here. So in fact that's the reason or the motivation behind working in the regime of resolved sideband regime, and this is experimentally speaking or practically it is it's a very good regime. Only issue is that because your kappa has to be much smaller, so therefore you really need a very good quality factor, a very high quality factor cavity. All these effects have been actually experimentally validated. This is some experiment that was done in the year 2008 by a group by Tufel group, and here you see, by the way, in this plot here, this omega m refers to our capital omega, the resonance frequency, and this omega here refers to delta omega, and this gamma refers to our symbol gamma, and this is the cooling effect. As we see, this is for the cooling and heating part, cooling and heating effect. This is your heating effect, and this is the cooling effect, and red dots are the experimental datas, and this solid curve is from the theory, and as you see the experiment and the theory matches pretty well. On the other hand, in this figure here is this is the frequency shift versus the detuning parameter, and here also you see the red one refers to the experimental datas and the solid curve refers to the theoretical plot, and both of them matches pretty well. And whatever we discussed, this feature is, as you can see, and this is actually done in the resolved sideband regime, and experiment and theory matches pretty well here. Now we are almost ready to discuss quantum regime. The quantum regime is particularly different from classical regime due to the so-called quantum noise. The quantum noise is generally discussed by the so-called quantum Langevin equations, quantum Langevin equations, and knowing this quantum Langevin equations is going to be very useful for us. In fact, to appreciate quantum Langevin equation, let us first discuss the classical Langevin equation. And to do that, we will begin with our age-old classical harmonic oscillator. And as you recall, that we represented a classical harmonic oscillator by the damped harmonic oscillator model, and we damped harmonic oscillator. Here I am going to discuss once again classical damped harmonic oscillator, and we'll see the shortcomings of the usual model. The equation of motion for the damped harmonic oscillator is this: m q double dot plus m gamma m q dot. This is the dissipation term, and we have m omega m square q is equal to 0. Just a caution here, gamma m is the same as gamma that just we have short while back we took, and omega m is the same as this resonance frequency omega for the mechanical oscillator, and this q is basically the same as x, the coordinate of the mechanical oscillator. So usually this is the damped harmonic oscillator equation, and in most situation it's all right, but there is a fundamental problem with this equation, because this equation is it is not time invariant. So not time invariant, and by this I mean that when you go from t to minus t, then this equation would become m q double dot minus m gamma m q dot plus m omega m square q is equal to 0. You see, this is because q double dot is d2 q dt2, so under time reversal it will remain the same, but q dot will change its signs because q dot is equal to dq dt. So if t goes to minus t, q dot would become minus q dot, and that's why this is what we are having. So physically what it means is this, that transfer of energy, this implies, because it is not time invariant, so transfer of energy is taking place. Transfer of energy is always from the oscillator to the environment, and the reverse process never occurs. And also you see here in this equation of motion for the damped harmonic oscillator, all the variables are in terms of the harmonic oscillator only, but it is generally, it interacts with the surrounding, and there is not a single variable apart from this gamma m which connects the dissipation of the oscillator, but there is no connection to the surrounding variables and so on. So therefore this equation is actually it's not correct in strict sense, because also you can see it from the solution of the equation, that solution of this, let me write the solution, and maybe you have already you must have studied in your undergraduate solution of damped harmonic oscillator. It's very easy to verify. If you can put this solution, you can check it that this solution satisfies the damped harmonic oscillator equation. So solution is like this: say q of t is equal to some constant, the amplitude a, e to the power minus gamma mt by 2, and you have sine omega m dash t plus a constant, this is phase of the oscillator, and omega m dash is the shifted frequency, and omega m dash is equal to, because of dissipation, you have omega m square minus gamma m square by 4. Okay, so by this you see the amplitude is of the oscillator is getting decreased as time goes on. So this solution says that for any initial conditions the displacement of the oscillator eventually decays to zero. However, such behavior does not represent realistically the situation when the oscillator is in thermal equilibrium with surrounding at a non-zero temperature. Say our this system is there and this system is surrounded by the environment, thermal environment. Thermal environment means it has some temperature T not equal to zero, and here by this the system in our case is the harmonic oscillator. Now if it is interacting with the environment at thermal equilibrium, the system is also going to have some temperature, so there is definitely going to be the displacement. So as time goes on this qt cannot go to zero. Actually that's what the solution says, but in reality that is not the case. If it is in thermal equilibrium, there will be always some kind of a displacement. So how to address this realistic case and to model the realistic situation, that means to take the thermal environment into account. What is considered is this, that okay, the system is interacting with the environment or the surrounding. Let me say this called environment, or it is also termed as BAT. Okay, it is called BAT or environment. This BAT is modeled as a collection of infinite number of independent harmonic oscillators. So this BAT is actually considered to be that as if this system is interacting with a lot of harmonic oscillator like this. These are independent harmonic oscillator. So and it is going to be modeled like this. So I'll show you how this is done. This is what is we are going to now consider, that this BAT is a collection of n independent harmonic oscillator, and the Hamiltonian for the system plus BAT can be written as follows. So let me write down the Hamiltonian first. Hamiltonian for system plus BAT. So why we are doing it? We are actually doing it so that we can have a realistic model of the interaction of the system with the environment, and the Hamiltonian would be like this. Say first of all the Hamiltonian, this part I'm going to write it for the system. So this is the kinetic energy. Let me consider the harmonic oscillator to be a single harmonic oscillator. So its momentum is P, mass is m, and you have half m omega m square q square. So this is the potential energy part, and the environment is now, or the BAT is considered to be a collection of n harmonic oscillator, let us say, and this would be all the oscillators has different momentum and different masses, and all of them are independent. So we have this sum of all this here, mi omega I square qi square, and this is the BAT part of the Hamiltonian. So let us say H BAT, and this is we have the system, which is our system harmonic oscillator, and the system and the BAT is interacting with each other, and the interaction is taken into account by this part here. Q is the system parameter, and the BAT parameter is there are n oscillators, and corresponding to these n oscillators there are qi number of coordinates. So various coordinates are there. So system coordinate is getting coupled to the BAT coordinates, and ci is the corresponding coupling between one particular BAT variable qi and system variable q. And there is an additional term that is added to these things just to take into account the or the cancel the shift in frequency of the system oscillator. You see frequency is associated with this q square, so this particular term is just added for convenient purpose so that it can cancel the shift in frequency of the system oscillator when it is interacting with the environment. So this is what is done. So we have a term like this. Okay, now from this Hamiltonian we can write down the first order differential equations for the path and the system variable. So you recall that the equation of motion we can write in terms of the Hamiltonian like this: say q dot j is equal to del h del pj, and we have pj dot that is equal to minus del h del qj. Okay, so using this we can write the equations for the system. Let me first write it for the system variable. That would be q dot is equal to p by m, and p dot is equal to, you can easily verify it, p dot is equal to minus m omega m square q plus summation I is equal to 1 to n ci qi, and we'll have minus q summation I is equal to 1 to n. Okay, let me take this here. Okay, let me write this part separately to avoid confusion. So I have minus q summation I is equal to 1 to n. I urge you to verify it whether we are writing it correctly or not. You can check it. So this is what one equation. Let me name this equation as, or let us say this is equation number 1. Let me make it equation number 2. This is equation number, say, 3. In fact, combining these two equations, rather I can write it this as mq double dot p dot, it would be equal to mq double dot, right? From here I can write p dot as mq double dot, and this would be mq double dot plus m omega m square q plus q summation ci square by mi omega I square, I is equal to 1 to n, and you have minus summation I is equal to 1 to n ci qi is equal to 0. So let us say this is my equation number 4. This is going to be a very important equation. We are going to come back to this equation a little bit later, and these are for the system. And for bath I have the equation as qi dot is equal to pi by m mi, I think, yes, and then we have pi dot is equal to minus mi omega I square qi plus ci q. Let us say this is my equation number 5, this is my equation number 6. So these are for the bath variables. Now solution to the bath equation, these bath equations can be easily written in terms of the initial bath variables, say qi of 0 and pi of 0 are the initial bath variables. Position and the momentum. Let us say at time t is equal to 0 we have qi 0, and at time t is equal to 0 we have momentum as pi 0. Suppose we know all these initial bath variables, then the solution can be written like this. So this is also you can verify just by directly putting it in the equations. So let me write down the solution here. So we'll have qi of 0, and we can have cos omega I t plus pi 0 by mi omega I. You may find it very difficult, but actually it is not difficult. It's a straightforward algebra only people do. But I think my motivation here or intention here is to do the things in details so that you can see the whole picture. Okay, let me do it. And you have Ci mi omega I integration 0 to t dt dash sine omega I t minus t dash, and then you have q t dash. Let me say this is equation number 7. Okay, now I want to do one thing. I want to put this equation number 7 in equation number 4 because I'm interested in knowing what's going on with the system. I have this system equation here. So putting this equation, so putting equation 7 in equation 4. Okay, let me write it down. You can actually take a pen and paper and do it yourself, and you can verify it. And let me just write down the whole thing here. This would be mq double dot plus m omega m square q minus I is equal to 1 to n ci square mi omega I. Okay, and integration 0 to t, and I will have dt dash sine omega I t minus t dash q of t dash plus q. Don't worry, it looks very difficult but intimidating, but actually it's we are going to simplify it, and we'll write a very simple expression at the end, and you will see that mi omega I square, and that is equal to, on the right hand side I will have I is equal to 1 to n ci, and you will have qi at 0 cos omega I t plus pi 0 divided by mi omega I, and I have sine omega I t. Okay, so now let's say this is my equation number 8. In fact, here you see this particular term, this third term in equation 8 on the left hand side. This can be simplified by using integration by parts, and if we do that, if we simplify it and put it in the equation 8 after simplification, that is very straightforward. And then if we do that, I can write this equation number 8 as follows. That would be mq double dot plus m omega m square q. Now the third term is simplified, so I will have I is equal to 1 to n ci square mi omega I square integration 0 to t dt dash q dot t dash cos omega I t minus t dash. Okay, and here I have on the right hand side I have I is equal to 1 to n ci. I think the same expression I am putting here. I will have qi 0 minus ci by mi omega I square q of 0, and this term actually coming after simplification of the third term, and we have here cos omega I t. Okay, and we'll also have this term. 1 minute, we'll have this term. This is what I'll have, plus pi of 0 by mi omega I sine omega I t. Okay, I'm doing the things in pretty details, but eventually we'll see we will simplify it further just by using some notation. Now the right hand side of this equation is important. This right hand side of this equation is due to the bath variables primarily, you see, and has the dimension of force, because mq double dot, right, that is force, and this term on the right hand side of this equation has dimension of force, and it is associated with the bath variables, and this is known as the Langevin force, and it is denoted by the symbol xi of t, and it is called Langevin noise. It is called Langevin noise, or it is called Langevin force also. Langevin force, and it arises completely due to the surrounding, and therefore under this simplification of this notation we can further simplify this equation, and we can write it as mq double dot plus m omega m square q plus m integration 0 to t dt dash gamma. I will define what this guy is, t minus t dash q dot t dash is equal to xi of t, and this is what we have as the so-called classical Langevin equation, and this is very important, and we'll see a lot of application of it very soon. And here this guy gamma t, it is a time dependent function. It is called a memory function. It is termed as memory function, and it is basically shorthand notation of this particular term here. Okay, let me write here, gamma of t is equal to 1 by m summation I is equal to 1 to n. We have ci square divided by mi omega I. Okay, and we have here cos omega I t, and this is termed as the memory function. Okay, this is it's a memory function, and I will talk about it all later, and it's termed as Langevin noise or Langevin force. Let me stop here for today. In this lecture we have discussed optomechanical cooling and optical spring effect using classical picture. Then we started discussing classical noise, because quantum noise distinguishes the classical regime, and to appreciate quantum noise better we have to first understand classical noise, and to do that we have derived the so-called classical Langevin equation. In the next lecture we'll discuss quantum Langevin equation. So see you in the next lecture. Thank you.